Today we're having as our guest speaker Dr. Krista Lilly, who is formerly Dr. Krista Ice, and she's an assistant professor in the Department of Biostatistics in the School of Public Health at West Virginia University, with a secondary appointment in pediatrics, where she works as the biostatistician of the Coronary Artery Risk Detection in Appalachian Communities Cardiac Project. Dr. Lilly received her PhD in psychology with an emphasis in both developmental and quantitative psychology from Vanderbilt University. She has experience working with parent-child interactions as a way to child achievement and health outcomes, and has applied statistical interests in factor analysis, structural equation modeling, and psychometrics. Dr. Lilly maintains a strong scholarship record with many conference presentations and co-authored published articles in Pediatrics, American Journal of Respiratory and Critical Care Medicine, and Archives of Internal Medicine. Furthermore, she has first author publications in other pediatric, obesity, psychology, and education journal. So we welcome Dr. Lilly and her presentation on structural equation modeling.
Thanks, Michael, for the intro and for inviting me here today. So today I'm going to be talking about structural equation modeling, and it's going to be a really introductory sort of talk. It's mostly just to kind of introduce you guys to some of the vocabulary and terminology. I'm going to introduce some really basic models, give you guys some formulas of both the measurement and the structural models underlying SEM, and you're going to understand some of the strengths and limitations of this analytic technique. So what you will not be able to do after hearing this lecture is be an expert in SEM or qualify you to use SEM without substantial support, and that's even if you did stay at a Holiday Inn Express last night. It's a very broad topic, and it's a tool used in a really broad number of disciplines. So you could take multiple classes on this and still not be an expert in this. So today's lecture is really just introductory sort of material. As with any other statistical tool or technique, you should work with someone with expertise or practice in its use, and you should always become familiar with the methodological literature before using it. So with those disclaimers in mind, I'm going to start talking about it now. So SEM, structural equation modeling, is also referred to by a bunch of different names, such as CSA, which is the covariance structure analysis, simultaneous equation modeling, path analysis, latent variable analysis. You can also do confirmatory factor analysis with it, and controversially, causal modeling. So I'm going to start with my first little sidebar here. So SEM can be used with a variety of different data, such as experimental, longitudinal, in addition to kind of the more typically used cross-sectional covariance sort of data. It was actually developed by geneticists and economists for the quantitative assessment of cause-effect relationships, which makes it really weird that most psychologists nowadays don't use SEM for demonstrating causal purposes. So you guys are probably sitting here asking yourselves, why don't I consider it a tool for demonstrating causality? I think Pearl sums it up really nicely in his 2009 book, that we currently sort of interpret SEM in terms of probabilistic information. In other words, those covariance matrices are really important to any sort of SEM structure, rather than the causal information that sort of underlies it. And the second generation of SEM researchers probably did this in order to gain respectability for SEM by keeping causal assumptions implicit rather than making those assumptions directly testable. And this is also probably caused by the fact that SEM is structured in algebraic language, which lacks the notational facility needed to make those causal assumptions explicit. So this is not to say that SEM should not be used to demonstrate causal relationships, just that as I talk about it and as other researchers usually talk about it, it's not really appropriate for its use. But Judea-Pearl actually does apply causal reasoning to SEM so that it can be used as it was originally intended. In other words, getting this causal information from these graphical models. So these causal claims in SEM can then be established through the use of this tool, along with that causal reasoning underlying it. But you can't do one without the other. You have to have both the causal theory and the tools involved in SEM before you can make those assumptions clear. So if you're interested in learning more about this, there's some really good texts on it. Of course, I'm quoting from Pearl here, but the Morgan and Winship book is pretty good too. So, and of course I can't give a presentation without throwing in some XKCD cartoon into it. So this isn't directly relatable, but you know, it's XKCD. So, all right. So let me rewind a little bit now that I've talked a little bit about causality and how I'm not real. Whenever I talk about causality in this lecture, I'm not really talking about the true causal relationships as a causal theorist might be talking about it. I'm more talking about in terms of the predictive variant aspects of it. So let's start off, though, by talking about the graphical aspect of SEM. So I've got two path models up here, and both of these are from an introductory SEM textbook. And this is just to kind of introduce you guys to some of the vocabulary involved in SEM. So in the first diagram, you can see up there we've got those variables A, B, and X. These are predicting or have the arrows leading to C, our downstream variable. A, B, and X can be referred to as exogenous, they're independent, they're source variables, they're upstream variables. C, or what we're trying to predict, our outcome of interest, is our endogenous variable. It's a dependent variable, it's downstream. We use a lot of different names for the same thing in this field. And now let's talk a little bit about those arrows. So you see a couple of different types of arrows here. We've got a double-headed arrow right here. This means that this is an association rather than a predictive path. The other ones are single-headed arrows, so A, B, and X lead directly to C. If you were to demonstrate this relationship over time, you'd get something that looks a little bit more like the path diagram down here, where you have A and B at time 1, A at time 2, leading to the final outcome of B at time 3. So you can see here we've added in some kind of, it looks like, if you're not familiar with SEM, just sort of random arrows floating around in here. But these are actually residual arrows, or they're causes residual to those explicitly identified in the diagram. And I'm going to talk a lot about these kind of mysterious error terms as we go through this lecture. In this case, I bring them up because I also want to note that they're also exogenous. So in this time-related model, you can see that there's a direct effect of A2 on B3. But there's no direct effect of A1 on B3. They're all indirectly related via B1 to A2 to B3, or A1 to B1 to B3, or A1 to A2 to B3. So there's a couple of different indirect paths that you can get A1 to get to B3, but there's no direct paths. So SEM is a really great tool for being able to pick up on some of these direct versus indirect causes. All right, so this is a model that starts introducing some of those boxes and circles you might have heard about if you know anything about SEM. So in this graphical model, we've got a couple of manifest variables. These are the known variables, and they're demonstrated by the boxes up here. So in this case, we've got three manifest variables. We have A, B, and D. In this case, A and B are our downstream variables, and D is our outcome, or our upstream variable. We also have this circle in here, and this is representing an unknown variable. It's something we don't directly measure. We try to get at via other measured variables. And this is a latent variable C. And it's kind of an introduction to path analysis. I have to start talking about identification of models. So in this model, we have three knowns, right? We have variable A, B, and D that are known, and we can get three correlations from A, B, and D. The correlation between A and B, the correlation between A and D, and the correlation between B and D. And there's no other known information in this model. We also have four unknown paths that we're trying to assign unique values to. And those paths are the lowercase a, b, c, and d in this case. Now D, right up there in between A and B, let's see if we can't get that going. So that one seems pretty easy to determine since we have the correlation between A and B, right? That's probably going to account for that D unknown path. But we also have these other paths leading to our outcomes. So we have A through A to the lowercase c going to D. And we also have that indirectly going through B down to C, down to D. We can try to account for this with A and D, but this also leaves the unknown paths of B and C and then D to A to C. So you can see here we've got these three unknowns and only two known correlations in which to try to interpret what those paths might be. In this case, no unique paths are, no unique solution is possible. This model is actually under-identified or under-determined, depending on what vocabulary you want to use for that. Okay, now if you remove path D, for example, this still gives us these same three correlations that we had before, and it leaves the three equations of lowercase a, lowercase b, and lowercase c. This model is now just identified, and if you're familiar with SEM terms, you'll know that this is also a saturated model. It means that all of the paths that we can currently account for are accounted for with those three correlations. Now, again, I'll talk a little bit more about this later on, but whenever we talk about model fit, this is a perfect model. This is a just identified model, but that doesn't make it a usable model. It's not a parsimonious model. In fact, it's the least simple model you can have because all of your degrees of freedom are used up. It uses the maximum amount of paths that you can possibly have in an SEM model. So what we really want to do is we want a model that's over-identified, such as the example that I have down here, by adding in another manifest variable, variable E. So now we have 4 manifest variables, which gives us 6 correlations, which means we can identify 5 unknown paths to have it still be over-identified. In this case, we have paths lowercase a, b, c, d, and now we have that new path added in of E. So whenever I talk about structural equation modeling with latent variables, this bottom model is the one I want to work with because I'm able to do more with it in order to come up with different testable models to figure out which the best model is. Okay, and this is a caution I give to everyone whenever you're talking about latent variable modeling, because we're going to talk about it in terms of the construct causing the measures, okay? So up here on the screen I have both of these are misspecified models. The first one looks right. It's got their latent variable, it's got arrows going down to 3 manifest variables, and whenever you think about this theoretically, you might say, well, I know that SES is made up of income, job status, and education levels. This is actually a misspecification because you might have people who if you have someone with high SES, they likely have high levels of all of these 3 things. But this is not necessarily the case once you get into talking about kind of a mid-level SES. A common academic example would be graduate students who are highly educated, but their job status is, they're graduate students, and their income level at the moment is not very high. So they might have a mid-level SES or low to mid-level SES, but this is not something that's consistent among the manifest variables that you see up there. Well, okay, so that's not right. So what might the appropriate latent model of SES look like? You might go to this next model. In this case, you can see that income, job, and education levels are leading to SES. So it's saying that SES is an emerging latent variable and it tacks some error on. This isn't appropriate either because SES is still not actually measured at all. What you should actually do with SES is do some sort of additive model or use these income, job, and other manifest variables separately within your model. A more appropriate model would be an example of this quality of life model. So I've shortened quality of life in order to fit in the little circle there. But it's made up of a patient report of their quality of life, their physician's report of their quality of life, and some sort of behavioral observation on behalf of the researcher. Now, someone with a high level of quality of life will have consistently high levels on all of these measures for it, but someone with a mid-level won't have a high patient report but a low physician and behavioral report. What you'll see is more consistent levels of these manifest variables. So you would have a mid-range patient report, a mid-range physician report, and a mid-range behavioral observation. So this is a much better, or a much more precise model of latent variable model of quality of life than we could get at with those SES manifest variables. Okay, so whenever we talk about structural equation modeling, we also have to talk about the measurement model and the structural model underlying it. There's always these 2 separate models associated with it. In this case, I'm going to theoretically work with someone who wants to predict quality of life with depression. And they go out and they get 3 different measures of quality of life for every person in the study. And they go out and they get 3 different measures of depression for every person in the study. In this case, we've got 2 different measurement models. We have one measurement model for quality of life and one measurement model for depression. And you might hear of the terms formal causes in the literature to kind of describe these measurement models underlying it. However, we also have the structural model, which is the actual paths that we're interested in testing, that quality of life predicting depression. And you can see here I've added some more of these mysterious little arrows floating around in space. So the one associated with the measurement models are different sorts of error left over after prediction of a measured variable, whereas we have this error coming off of depression, and that's our D, or disturbance, variance left over after prediction of a factor. Okay, I said before I'd talk a little bit more about the mysterious E term. So we call it a bunch of different things. I mentioned just now, error terms, disturbances, but we also call them residuals or nuisance variables, and it refers to all the other stuff that affects downstream variables not explicitly represented in the model. And in some ways, this allows SEM to be a pretty flexible program because we can account for certain errors to be correlated. For example, in that previous example I gave you, we might decide to correlate the patient reports, assuming that patients might more consistently respond in a way than their PCPs or the researchers might. With that in mind, there are some limitations to what the error can pick up because it's not picking up any sort of it's trying to pick up the random error associated with your model. If you have any sort of systematic error, that's still going to go through the other paths. It's not going to accurately be demonstrated within this mysterious E term. I'm going to start throwing some Greek letters names at you guys because that's how I learned. I learned through literal notation, so you guys get to learn that way as well. So just to start kind of introducing you guys to some of this terminology, whenever I talk about theta delta errors, those are always the errors associated with the measurement model on X. Theta epsilons are the errors associated with the measurement model on Y, and then I talk about the zeta errors within the structural model. Now, again, all of SEM is kind of based in this matrix algebra understanding, and so I'm going to try to integrate some really basic stuff. I'm not going to have this be an introduction to matrix algebra in addition to an introduction to SEM. So if there's some of this matrix algebra that's a little bit confusing and stuff, I apologize ahead of time. But so you guys have seen this like simple regression equation that I've had up here before. So we've got our y equaling gamma x plus our zeta term. We know that the covariance matrix associated with that is this kind of standard matrix where we have the variance here, and then the of y there, the variance of x here, and then the covariances on the off diagonals. If we were to kind of integrate this understanding of the covariance matrix into that regression, we wind up with something that looks a little bit more like this, where you can see the variances associated with gamma and zeta are introduced into the top left-hand corner of the matrix. And now we're mostly focused on this x, or outcome or the predictor variable, because we don't really know anything about y at this point in time. Okay, so again, remember I'm going to keep talking about measurement models in addition to structural models. It's never just one model. I'm going to be using some matrix algebra shorthand and some other kind of important Greek letters to throw at you guys. Whenever I talk about Psi, that's the exogenous latent variable. Eta is our endogenous latent. Gamma are the beta weights regressing eta on Psi, and even though my example doesn't use any betas, if you hear a SEM person talk about betas, these are the beta weights associated regressing an eta on another eta. So in the example I just gave you, if I were to put this into literal notation, what I'm actually talking about are the first measurement model of quality of life being that Psi variable, with the lambda x's 1, 2, and 3 predicting the manifest variables of 1, 2, and 3, and the errors associated with that being the theta epsilons 1, 2, and 3. Whenever I'm thinking about the depression measurement model, that's our eta variable in this case, and it represents the paths leading to manifest variables y1, y2, and y3 with lambda y's, and has errors theta deltas associated with it. And then our structural model is actually that Psi leading to the eta, using the gamma path with the zeta error term associated with it. And here are just the written out, again, I wrote them out in English because I was getting a little tired of trying to hunt and peck for all the Greek letters in my slides, so I apologize about that. But The measurement model for y is equaling tau y, which is our intercept term in this case, plus the lambda y's times the eta, plus the error terms. So you can see how this is trying to follow that basic regression form that you guys are used to seeing. We have a separate measurement model for x that looks pretty similar, and then we have our structural model, which is now eta equaling alpha, which is the intercept, plus gamma times psi plus theta. So you can make models way more complex than the really simple one I gave you, and this is just throwing up the Lizral reference sheet, so it's not there to scare you guys or anything like that. It's just to let you know that resources are out there to help you set up your model appropriately in terms of the covariance structures, the measurement models, and the mean structures associated with any of those larger, more complex models. So some of you in the audience, maybe some of my students perhaps, might be looking at this going, blah, math. I don't really want to relearn matrix algebra. I learned that a while ago and I don't remember any more of it. Do I really have to do it in order to run an SEM model? And my answer, of course, is, well, yes. You have a bunch of different matrices and covariance matrices. You can underlie a mean covariance matrix underneath the covariance matrix. All of these require you to have a really fundamental understanding of matrix algebra and what paths need to be constrained and what paths don't need to be. And this is true even if you use a fairly basic program like AMOS, which basically lets you draw lines to boxes, and it can get you in a lot of trouble if you don't know what you're doing. Obviously, I've used AMOS before. It's not that it's a bad program. I just don't think it's very flexible in terms of being able to adapt your matrices according to what model it is that you want to run. So I recommend other programs that allow you to actually specify the underlying matrix algebra, such as Lizral, which is what I was trained in. I use M+ a lot now because it's a pretty straightforward program to use and has really great missing data capabilities because it uses full information maximum likelihood and allows you to enter in auxiliary variables and stuff. So I really enjoy using M+. SAS has recently got their Calus and TCalus packages up and running. I haven't played around with that a lot, but I look forward to learning a lot more about that one. R packages, I've dabbled a little bit in R, so I can do some SEM and Levant in that one. There's plenty of other packages out there that will also run SEM models, such as Stata, Statistica, EQS. Again, I mostly use M+ or Lizral, but there are other programs are out there that I think would also do an excellent job. Okay, so I've talked a little bit about what a measurement model is, what a structural model is, through some matrix algebra formulas at you guys. Now I'm going to talk about what happens after we get run this all through one of those programs that I was just talking about, and we get some output on a page, and we have to try to interpret what that means. So what we do whenever we try to assess an SEM model is we try to assess something called model fit. And that usually refers to the ability of the model to reproduce the data, or in other words, usually that variance-covariance matrix that I'm mostly vested in looking at. A good fitting model is one that is reasonably consistent with the data and does not require respecification. However, good fit indices or a good fitting model can always, may be able to be improved upon. Just because you find a good fitting model doesn't mean it's the best model out there or it's a perfect model. It does not prove the model is correctly specified or valid. For example, a model all of whose parameters are 0 is actually a good fitting model according to a lot of different fit indices. So, and additionally, models with nonsensical results such as paths that are clearly the wrong sign showing some suppression or something going on, models with poor discriminant validity or Haywood cases, these can all actually wind up with really great fit indices. So this is a little unfortunate. But let me talk a little bit more about what these fit indices are before I start talking more about the limitations of SEM. So the first thing you do is you fit the omnibus model to a chi-square. As most of you know, there's a pretty strong link between chi-squares and sample size. So that led researchers to go, well, we can't just look at this chi-square because anytime I have a sample size bigger than 200, it's significant, and we don't want a significant p-value here. So what else can I look at? There are 3 different fit indices that have currently been developed. The first is incremental fit. It's the most often used one. It's somewhat similar to an R-square if you're thinking about it in terms of standard regression. An example of this is the normed fit index, NFI. but really there's hundreds to pick from. This is just one that Lizroll tends to use, so I've learned about it, but there are hundreds of different incremental fit indices that you could fit to this model. In this case, the formula is the chi-square of the null model, meaning that we are not allowed any structural paths within our model, minus the proposed model that you're invested in looking at, and you're dividing by the chi-square of the null model. And whenever you have this sort of value, anything above a 0.95 is considered a good fitting model. And this is a pretty common rule of thumb for all of the incremental fit indices. You usually want something that's above 0.90 or 0.95. You want it to be pretty close to 1. The next type of fit indices I'm going to talk about is this absolute fit, or the badness of fit. So a really common example of this one is the RMSEA, or the root mean square error of approximation. And that's calculated by looking at the square root of the chi-square of the proposed model minus degrees of freedom divided by degrees of freedom times n minus 1. In this case, we want something really small. We're trying to minimize the amount of error within our model. So something less than 0.05 is typically considered a good fitting model. And again, there's plenty of other fit indices out here. I'm going to talk about SRMR here in a minute. The final type of fit indices is, I think, really gets at the power that you can get out of an SEM model, and that allows you to do nested model comparisons. So an example of this would be the AIC, and that is, it's a measure associated with the chi-square value. And in this case, lower values indicate better fit. But the really cool thing about this is that if you just run an AIC on a single model, it gives you a number. The number doesn't really mean anything. But whenever you compare it against the nested models that you're looking at, this is where you can start figuring out what the best model is for your particular data set. Okay, so this is a short example I just used in class because I was taught by David Cole. So he was a clinical psychologist, and he was invested in looking at depression, which is why a lot of my examples here deal with depression, not because I'm depressed. So in this particular model, we've got 101 people who decided to participate in the study. They all answered 3 questionnaires and 2 clinician ratings about their depression levels. In matrix algebra short and longhand, you can see this up here is designating the paths that I'm interested in looking at with this model. So I have 5 manifest variables, which is going to equal the paths from depression down to the scale. In this case, these are lambdas, and they're Q by N matrix. So that means the number of manifest variables by the number of latent variables that I'm interested in looking at. We're going to do that times the epsilon, or in this case, the vector of latent constructs. We just have 1 in this case, which makes it a pretty straightforward model. And we're going to add in those error terms. And again, the error terms are the theta deltas all off the manifest variables. So if I were to run that through Lizroll programming, which is what I did in this particular case, I came up with a bunch of different fit indices. So I just grabbed a few out for you guys to look at. In this case, we came up with a significant chi-square. We prefer to have our chi-square value be somewhat more similar to our degrees of freedom, and for it not to be significant, obviously, then. And we're going to look at a couple of different fit indices. So here's our RMSEA that I just mentioned that we wanted below 0.05. In this case, it's actually pretty high at 0.32. Our SRMR, which is a different sort of measure for the same thing, is much lower and actually more in the rule of thumb appropriate terms. So, you know, RMSEA is not great, but the SRMR is okay. And then we look at the CFI and the GFI, which are similar to the NFI presented to you just a second ago. Again, we want these above 0.90, 0.95. So the CFI is not bad, but the GFI is not really good either. So everything that I'm kind of reading from this sort of output is telling me this is not a great model. There's probably ways that we can improve upon it. You don't want to interpret the lambdas associated with it until after you have a better fitting model. But in this case, I went ahead and looked at these lambdas just to kind of figure out what it was looking like and what I might be able to do next. In this case, I knew that theoretically I had 3 of these scales that were reported by the same person, and then 2 others that were reported by 2 other individuals. And you can kind of see that reflected within these lambdas. You can see that these are a little bit lower consistently, and these are a bit higher consistently. So my next step might be to try to do a 2-factor solution and compare the models. We start running into some identification issues if I try to do that. So I think the moral of this story is try to get at least 3 measures per each of your latent variable, and if you wind up with less than that, it makes it really hard to test any sort of nested models within this. So to kind of run through the steps of everything we just did, and this is again just pulled from another introductory textbook, the first thing you want to do is again specify those model, making sure you have your measurement model and your structural model set out correctly. You usually want to diagram it out in terms of graphical terms, especially if you want to underlay it with any sort of causal reasoning behind it. Next thing you want to figure out is that identification. That's so important. We want it to be over-identified. Without over-identification, we don't find these unique estimations assigned to every model parameter. So identification is very important with SEM models. Of course, then you select the measures. You want to make sure you have reliable and valid measures because SEM will not make up for poor data. You want to collect the data, analyze it, and evaluate it in the terms that I was just talking about. And then you always go through step 6 a couple of times, 4, 5, and 6 a couple of times, because you always want to re-specify that model and evaluate the fit of the revised model and do some model fit comparisons. I also, even though Klein didn't mention this, I also argue that checking the model assumptions prior to this analysis and prior to collecting data, you might decide to do a Monte Carlo simulation to figure out what your sample size should be according to a certain power estimate. Okay, so now that you guys have a brief introduction to SEM with some of the vocabulary associated with it, I'm going to start talking about the assumptions and limitations and, of course, what SEM is good at. So in this case, you can see that whenever I talk about SEM, I really love using it in terms of being able to specify latent variable models where I can provide these separate measurement and structural models. This allows us to assess the psychometric properties of measures and estimate the relations among constructs that are corrected for bias attributable to random error and construct irrelevant variance. And of course, this is with the underlying assumption, note here that this is within certain parameters and, of course, all the normality assumptions we're going to talk about in a second. So SEM, I think, is really cool because it gives you a bunch of these global fit indices that tell you if your models fit in the variance-covariance matrix appropriately. It's really a neat way for summarizing a large number of complex equations into a single number, right? It also allows for model comparisons, which I think is pretty important. Tamarkin and Waller, who is also trained by, also suggest another strength lies in directly testing the model of interest rather than a straw man alternative. And it allows for a flexible array of possible covariance structures, which is pretty neat for modeling random effects and residuals. And whenever I'm talking about it in terms of comparison to what else you could be doing, in terms of many alternative or traditional techniques, they might not be as flexible or as all-encompassing and able to get all of these different equations within a single model. For example, SEM provides an advantage whenever we're talking about the traditional repeated measures approach because it can do some really nice latent growth modeling and allow for multi-level modeling capabilities. It gives you improved statistical power over standard multiple regression, and it gives you access to better methods for treatment of missing data depending on what program you're using. I mentioned I really enjoy using M+ because it has great FIML capability. Certain software can take into account complex survey data, which is pretty important. And under particular conditions and assumptions, SEM can provide analytically equivalent models to other modern modeling methods. So it's definitely proven over traditional methods in terms of other modern methods. It can at least do as good of a job as some other ones under particular conditions and assumptions. There is always exciting new developments being made for SEM modeling, particularly in terms of categorical, observed, and latent variables. And a lot of new software has come out that has really increasingly diverse applications to a bunch of different fields. However, let's start talking about some of the limitations to this. Although mathematically and computationally complex, it's become increasingly accessible to researchers who lack specialized statistical training. Steiger is another person I was trained under, and he actually developed the RMSEA, and he would hate it whenever anyone would use AMOS for this reason. Newer methods within SEM are not fully tested under assumption violations, and we're going to talk about a little bit more about those here in a second, but this is particularly true under model misspecification, linearity, and normality violations. All right, so let's start talking about some of the restrictions to what you can do with SEM. So SEM is built on this kind of traditional GLM, general linear modeling framework, and it relies on all these normal theory methods, maximum likelihood, for example, when testing model parameters and testing models' goodness of fit. In other words, this really assumes multivariate normal data. This is great when you have multivariate normal data and you have a correctly specified model, since parameters will be asymptotically unbiased with large samples in particular, asymptotically efficient with large samples in particular, and consistent as the sample size increases. So you shouldn't get a vastly changed model if you add more people to your sample or not. But whenever you don't have those two things, a lot of stuff can go wrong. For example, you can have high type 2 error rate. Your standard errors are going to be attenuated, of course. It can lead to extraction of spurious latent variables, particularly whenever we're talking about growth models. So there are ways around this, right? So there's pretty substantial research on asymptotic robustness theory describing some conditions in which this modeling technique is more robust than others might be. But again, there's no red flag that's going to tell us whenever you violated these assumptions. These are something you have to test beforehand, because you're just it's going to spit out output, and it's going to look like you have a great fitting model whenever you've actually had your standard errors attenuated or something like that. In the event of non-normal data, there are, again, techniques out there that can help you deal with that sort of, such as weighted least squares, maximum likelihood corrections, bootstrapping methods. But they're still sort of being combined with the SEM literature, and they all have their own particular needs and requirements, which should be explored fully before using them within SEM. Omitting variables is just, or model misspecification in general, is can cause a bunch of issues with your SEM model, including leading to misleading measurement or causal structures. Results in biased parameter estimates, inaccurate estimates of standard errors. And a lot of people think that by including that magic error term, we've magically fixed all of these issues because, oh, we have a place for all that variance to be shoved to, right? It can just be found over in that E term. Well, if it's systematic error, it's not going to go over into that magic E term. That magic E term only picks up the residuals that are not systematic. So whenever I talk about this, it's in terms of the covariances among residuals to note the omitted common causes. All right, just because a model fit well doesn't mean it's a good model. I hope I've kind of pounded that into your head by now. You might still have omitted variables or other specification errors associated with it. And some people say that another limitation of SEM is that it can kind of make you ignore or neglect some of the lower order model components. So we're so focused on this omnibus model fit test that sometimes we forget to make sure that we have accounted for appropriate amount of variance, for example, in our measurement model. So a well-fitting model due to a well-specified measurement can still account for low variance in endogenous variables. In other words, it's actually not a great model. We're not accounting for that much variance in our outcome measure, but wow, we measured that predictor really well, you know, and the model fit will pick up on that. So to kind of pound this point home, your parameter estimates and associated standard errors are going to be unbiased only under the assumption that the specified model is correct. If you make an error or omit a variable or something really early on or upstream in your model, it only gets worse the further you go downstream. So if you were to do a traditional sort of standard regression technique, this would actually protect against this sort of issue to where you'd be running these separate models. In SEM, you make one little error upstream, it's going to affect the entire model. Some other common user errors that can usually occur include forgetting that the statistical theory underlying SEM pertains to covariances rather than correlation matrices. This was particularly a problem whenever the SEM field was getting up and going by psychologists, because they would often kind of confuse the terms, and they would input things like correlation matrices instead of the covariance matrix, which of course causes huge issues with your model. There might be alternative models out there that fit the data equally well, and again, there's no red flag that's going to pop up and tell you that this is a good fitting model, but there's something better out there, so it's up to the researcher to remember to always explore other model fitting options. Lack of understanding of the math underlying measurement and structural models can be a huge issue, particularly when you just use Amos and you throw boxes with circles and arrows connecting them. I think there are too many rules of thumb being used that aren't based on any sort of literature. They're just sort of based on people's gut feelings, which I think is usually a bad idea. For example, a lot of times if you go to an SEM class, they'll say, oh, a sample size of like 200 is great. But that might not always be the case. It really is just sort of a number being thrown out there. It seemed sort of like a big one to researchers at the time. The cutoffs fit for good model fit, I already mentioned before, were just sort of like 0.05 or 0.90. They sound great. They're not really based on any sort of literature. SEM cannot compensate for limitations in study design or method. That's really important to note. And the theoretical model does not always translate to a structural one. This is something I have a huge issue with whenever a theoretical model is proposed. A lot of times we'll try to submit that for publication in the psych field at least, and they'll say, oh, why didn't you just run an SEM on it? You have a model. You should test it. While I agree you should always test a model, I think that's important, it might take a little bit of translate in order to make that theoretical model become one that you can test using SEM. Okay, so that was the end of my lecture. I've got some great references here that I've really relied upon to make this lecture up. So if you're interested in learning more about SEM, this is a really good starting place for you.